Alright guys, let's continue working through this problem. Again, don't stress yourself out too much about surrounding and system. I think that's going to come a little bit, or will be a little bit easier as we work through some of these problems. So the first thing we have to recognize is we're using this Q equals MC delta T, where M is mass, C is specific heat capacity, and T is change in temperature. So the first thing we want to do is find the mass of the solution. Well, how do we do that? Well, the first thing we want to do is recognize that for the most part, the density of water and the density of aqueous solutions is usually around 1 gram per milliliter. And this stays pretty well true for almost all solutions, all aqueous solutions, I should say, and for pure water. And this a lot of times will be given to you. It's just not given to you in this problem, probably because of how I copied it down. So what we need to recognize is that if we have 50 milliliters of hydrochloric acid and we have 50 milliliters of a sodium hydroxide solution, we have 100 milliliters altogether. Well, for every 100 milliliters, or for every 1 milliliter, we have 1 gram. So for 100 milliliters, we're going to have 100 grams of solution. Okay, specific heat capacity is 4.18. Again, this is true for pure water as well as most solutions. If there's a difference, they'll give it to you. And change in temperature, we're going from 25 degrees Celsius for both of them to 31.9 degrees Celsius. Now, this would be a lot more complex if we were dealing with two temperature changes, meaning both solutions started at different temperatures. But because they're both starting at 25, they're going to 31.9. That makes our life a little bit easier. It means our temperature change is 6.9. Okay, so now all we have to do is calculate this out. So we have 100 times 4.18 times 6.9, and we have a Q equal to, two proper sig figs, 2,900 joules. Now, is this positive or is this negative? This is where things get a little bit interesting when you're working through solving these problems. First off, we have to recognize that the temperature increased. Specifically the temperature of the solution, water, however you want to think about it. That means energy was released. If energy is released, that means our Q is exothermic, which means it's automatically going to be negative. Let's clean that up just a little bit. So Q is going to be equal to a negative 2,900 joules. Okay, and again, I know that's a little bit weird to think about, but again, that's because the temperature we're measuring is of the water. Water, in essence, is really kind of the surrounding in this regard, and the system is the reaction itself, but the reaction's also occurring in the water. So again, gets a little bit ambiguous here. So we have to recognize that, okay, the surrounding is increasing temperature because the reaction is releasing energy, therefore Q of the reaction is going to be negative, exothermic. Okay? All right, let's keep going. Okay, what I want you to do, this is a very similar problem. I want you to pause and calculate it for yourself. See what you come up with. Okay, and this one, keep in mind, is a little bit more complex due to this molar enthalpy. Don't worry about that right now. I will show you how to do that as soon as we're done with this problem. What I want you to do is identify your surroundings, your systems. Again, this is going to be a little convoluted here, a little ambiguous because we do have a solution going on. I want you to write your net ionic equation, yes, a blast from your past. And I want you to calculate Q as well for this problem. And then we're going to come back and talk about this molar enthalpy idea in just a second. So pause, see what you come up with. All right, let's talk about it. So we have surrounding and system. So the reaction in technicalities is the system. That's what we want to measure. That's what we're looking at. However, it's occurring in water, which is both acting as the system and the surroundings. And what I mean by that is we're putting the thermometer in the water, which is where the solution's occurring, and the energy from the reaction is being transferred to the water. So in other words, we're going from 25 degrees Celsius to 28.1 degrees Celsius. Energy is increasing in the water, which means the reaction is releasing energy. So again, this is where things get a little bit interesting. Water is kind of acting as both the surrounding and the system. And that's because the reaction is occurring in the water. But we're measuring the temperature of the water. So that means we're kind of measuring the surrounding, or measuring the temperature change of the surrounding. Surrounding is increasing temperature. System is therefore losing energy. Net ionic equation is pretty straightforward here. We are going to have barium plus 2 reacting with sulfate minus 2 to form barium sulfate. And just as a reminder, how we write a net ionic equation is we break things down that are aqueous. So both sodium sulfate and barium nitrate are aqueous. So we end up with barium plus 2 nitrates, plus 2 sodiums plus 1 sulfate, going to barium sulfate, which is a solid, plus 2 sodiums and 2 nitrates. Okay, and remember, we get rid of what's the same on both sides, so our 2 nitrates and 2 sodiums disappear, and what we're left with is the barium ion, the sulfate ion forming barium sulfate. Okay, so from there we calculate our Q value. Okay, we use our MCAT equation for that. So Q equals MC delta T, where N is the mass, and again we're going to use our volume here, recognizing that is a aqueous solution, so our density is 1 gram per milliliter, and really just 1 gram, not 1.00. Okay, so we have 1 liter, which is 1,000 milliliters, plus another 1 liter, which is another 1,000 milliliters. So we have 2,000 milliliters, which means for every milliliter we have 1 gram. So we have 2,000 grams of solution here as our mass. Our specific heat capacity is 4.18, and our change in temperature is the 25 to the 28.1, which means we have a 3.1 degree temperature change here. Okay, and we calculate our Q accordingly. And keep in mind, we have a really small temperature change here. I want you to think about why that's the case. Why would our temperature change be so small for this particular solution versus the last one where we had a little bit bigger temperature change? Okay, and the reason is because we have so much water. We have 2,000 grams of water. Remember, water's got a very high specific heat capacity, which means a lot of energy being produced for a lot of water is still not going to change its temperature very much. Let me try that again. For every gram of water, it takes 4 joules. So if we have 2,000 grams, it is going to take 8,000 joules to change it by 1 degree Celsius, if that makes a little bit more sense of that. Okay? So we have a very low temperature change for that reason. Now, our Q ends up being, in this case, with 2 proper sig figs. It actually looks like we should have 3 proper sig figs, looking at all of our numbers in our problem, so we'll do 3 sig figs, is going to be 25,900 joules. That's how much energy it takes to change 2,000 grams of water by 3 degrees Celsius. Okay? Now, from there, we're not done yet. This just gives us our Q value. Okay? It wants to know molar enthalpy. Well, what in the world does that mean? Molar always means per 1 mole, and we'll be doing a lot of this throughout this chapter. So we're looking at the energy for 1 mole of reactants, okay? Or not specifically of reactants, but of the barium sulfate. Okay, so what that means is we need to figure out how much barium sulfate was actually formed in this reaction, which means, you guessed it, a little bit of stoichiometry, okay? So we're starting with 1 molar of each of these in 1 liter. The nice thing is it's already a 1-to-1 ratio, so they are both reacting completely. You're welcome to do the limiting reactant if you want to. And because we have 1 liter, 1 molar, we have 1 mole of each of these. So again, you're welcome to do the limiting reactants and work through that if you want, or you can recognize that we have a 1-to-1 ratio, 1 mole reacting with 1 mole, which means we are creating 1 mole of barium sulfate. So this amount of energy being produced is being produced from the formation of 1 mole of barium sulfate. So if we wanted to find molar enthalpy, which by the way is always in kilojoules per mole, okay, the first thing we have to do is convert this into kilojoules, which is going to be 25.9 kilojoules, divide by the amount of moles, which is 1 here, and that gives us a molar enthalpy of 25.9 kilojoules per mole. Now, that one's pretty straightforward, but let's say we were dealing with a different problem, and let's say instead of 1 mole, we only had 0.5 moles of barium sulfate being formed. Okay, for this 25.9 kilojoules, what does that mean? It means we take the 25.9 kilojoules, divide it by that 0.9 moles, and that number we get is going to be our molar enthalpy. In this case, 25.9 multiplied by 2 or divided by 0.5, however you want to think about it, is going to be 51.8 kilojoules per mole. So just remember, this is a number we just made up. This is not actually part of the problem. I'm just showing you what happens here if it wasn't a 1-to-1 mole ratio, or we weren't just forming 1 mole. So that's all molar enthalpy is. Anytime you see the word molar, like let's say molar mass is one you've already seen before, that is a mass per 1 mole of that substance. Molar enthalpy is the amount of energy released for 1 mole of that substance being formed or used, depending on how we're looking at the problem. So molar just means per 1 mole. Enthalpy is energy, so it's the amount of energy produced for 1 mole of that substance, in this case barium sulfate. And we're only forming 1 mole just due to our numbers here. Okay, and we'll work through more of those as we work through these problems as well. Okay, let's keep going. Next thing is bomb calorimetry. You're not going to see a lot of this, but it does show up. So let's kind of talk about what in the world this is. It is still calorimetry, but instead of using a styrofoam cup, you're dealing with basically a machine, or not a machine, a piece of equipment that's already been created and already been standardized, meaning you have kind of like a little container inside a tub of water, if you will, and they measure the amount of energy changed for the water as well as the container where the reaction's occurring. And it's exactly what it sounds like, a bomb calorimetry. So it is a combustion occurring inside this little container and then water surrounding that container inside of another container. So kind of think about it this way. We have a container, we have water around that container, and that's enclosed inside of a container. So they take something with a known amount of energy being produced, they burn it inside this container, and they measure the amount of energy being released into that water, and they get what is known as a specific heat capacity for this piece of equipment. So if we're reading through this problem, we have 0.5269 gram sample of octane is placed into a bomb calorimeter, which has a heat capacity of 11.3 kilojoules per degree Celsius. So notice grams are gone here. Why are grams gone? Grams are gone because it's already standardized for the mass that is being produced in this solution. Or not solution, in this piece of equipment. And again, that's only for this piece of equipment. Okay? What that means is 11.3 kilojoules of energy is required to raise the temperature of this whole piece of equipment by 1 degree Celsius. Okay? The octane is ignited in the presence of excess oxygen, and the temperature increases the calorimeter to 2.25 degrees Celsius. So a bomb calorimeter equation is a little bit different. It's Q equals delta T times C, and the reason why grams are gone is because, again, standardized C value. So pretty straightforward to calculate here. We have a change in temperature of 2.25, so the temperature increase of the calorimeter is 2.25, so we don't have to do any math there. So Q equals 2.25 times a specific heat capacity of 11.3 kilojoules per degree Celsius, and we get a Q value of 11.3 times 2.25, 3 proper sig figs, 25.4 kilojoules. Now, that is the amount of energy gained by the piece of equipment. So how much energy was actually released by the combustion of the octane? So the temperature of the calorimeter goes up. That means the energy released, or energy is being released by the combustion of the octane, which means its Q is the same value, but negative. Okay, because remember, energy released is the same amount of energy absorbed. We're calculating the amount of energy absorbed by the bomb calorimeter, and we are going to just convert that into a negative sign for the amount of energy released by the combustion. Okay, so that's bomb calorimetry. Pretty easy, straightforward, a little bit less convoluted than some of the other equations. Okay, so what I want you to do is, you're going to have some calorimetry problems to work on the rest of today, but what I want you to do is, since we've already talked about molar enthalpy, I want you to check out this problem and see if you can solve it, and we will come back and talk about that in the next videos. And I guess that's it. Thanks, guys.